So in today's lesson, we will be dealing with static electricity. Before starting the theoretical part of this lesson, I suggest that you halt this video and visit this link. This is a great introduction to the topic static electricity. I also suggest that you visit this link So, what is static electricity and how different is it to the electricity we use to power our homes? So, as the word, or rather as the title implies, static means not moving, whereas the electricity that we use in our homes is current electricity, where you have movement of charge passing through the wires. We've met with different situations involving static electricity in our lives. For example, you might be removing a woolen pullover and you feel or hear sparks or crackles. You might rub a pen against your sleeve and then you place it near tiny pieces of paper and they stick to it. Or else, after a long drive, you touch the handle of a door and you feel a shock. These are all situations of static electricity. Before actually going into the theory of why this happens, it is very important that we revise and we go through the structure of the atom. So as we all know, all matter is made up of atoms. If we consider an atom, it is in turn made up of smaller particles called protons, electrons, and neutrons. So at the center of the atom, there is what we call the nucleus. So the nucleus is made up of protons and neutrons. Protons have a positive charge, whereas neutrons, as the name implies, are neutral. They do not have a charge. As regards size or mass, they are quite similar to each other. Next, we have the electron, which is much smaller. In fact, if we look at the diagram shown, that is definitely not a scale. In an atom, the number of protons equals the number of electrons, so the atom overall has no charge. This is an animation of what we imagine an atom to be like. So you have the protons and the neutrons at the center, and you have electrons orbiting the atom on the outside. When you have two opposing charges, so you have a positive charge and a negative charge, they attract each other. When two charges are alike, so you have a negative charge and a negative charge, they repel each other. So they try to move away from each other as much as possible. The same applies for a positive charge and another positive charge. When you have two neutral objects, you have neither repulsion nor attraction. So we know that there are electrical conductors and electrical insulators. Charge can move through certain materials, but not through others. So in insulators, electrons are tightly held to their atoms, and they are not free to move when a potential difference is applied. So when insulators are charged by rubbing, electrons can be transferred from one material to the other, since they are being given the necessary energy for transfer. When an insulator such as polythene or perspex are charged by rubbing, they will retain their charge. So basically, when you have an insulator, charges cannot travel through it. You can charge an insulator by a process called rubbing, which we will go into further detail later on. But once an insulator is charged, the charge is retained. It cannot escape. It cannot move from one end to the other. Whereas in the case of conductors, we have materials, such as metals for instance, which have free electrons, and these, since they are not tightly bound, can flow through the material itself. Since free electrons can readily move from one object to another, conductors lose their charge immediately. When charged through rubbing, the charge can be lost either through the hand or any other surrounding material. So if I have a metal rod and I charge it by rubbing, as I explained in the case of insulators, the charge will immediately be lost because it can travel through my hand and to earth. This obviously cannot happen in the case of insulators. So to summarize the slide, when you have an insulator, charge cannot pass through it. It cannot travel. In the case of conductors, charge can travel from one end to another easily. You can charge insulators by rubbing, but you cannot use the same method to charge conductors. So here we have a quick summary of what we've just said. So in the case of electrical insulators, charged particles are not free to move about, whereas in the case of electrical conductors, charged particles are free to move about. So electrical insulators cannot conduct electricity, whereas electrical conductors can conduct it. In order to charge an insulator, you can charge by a method of rubbing or by friction. In the case of conductors, you can charge a conductor by a method of induction. We will discuss these two further on. Some examples of electrical insulators are glass, perspex, silk, and wool. Some examples of electrical conductors are copper, steel, fluids which have immobile charged particles, like for instance water. Insulators can be charged by rubbing as the charges remain in place. However, conductors cannot be charged by rubbing since charge is lost immediately, especially if it is in contact with another item. So once again, I suggest that you halt this video and visit this website. There you find an activity related to conductors and insulators, which I highly suggest that you try out. Next, here I have some examples of different materials. I will give you some time to write down the answers on a piece of paper where you are given the task of sorting these into conductors and insulators. Please hold this video while you do this task. So, for the solutions. Iron is a metal and it is a conductor. Copper is also a conductor. In fact, the wires in our homes are made of copper. Perspex is an insulator. Steel is a conductor. Acetate is an insulator. Rock is an insulator. Paper is an insulator. And graphite is a conductor. Remember, all metals are conductors, but not all conductors are metals. For example, graphite is not a metal, yet it is a conductor. Water is not a metal, and it is a conductor as well. Our own bodies are not metal, but we are conductors of electricity. So here I have an example which we can go through as a revision of what we stated earlier on. When the following charges are brought close together, do they attract or repel each other? So in part A, we have two positive charges. In this case, since we have like charges, they repel. In part B, we also have like charges, but in this case, we have two negative charges. Here, once more, we have repulsion. In part C, we have unlike charges. We have a positive and a negative charge. These attract each other.